Okay, yeah. So we saw what happened if we call this function here. And here I had it counting. In fact, I'm just going to comment this out. And I mean, let's even ignore whatever we're passing to it. We're just calling this function uh-oh. And what does this function uh-oh do? Well, all it does is print out. Actually, it does nothing. It prints out. I'll put this back in. Oh my goodness, apparently copying is just too much. All right. Actually, I don't even need this. I won't do this. Okay. So all we're doing is here's a function called uh-oh. And what's it do? Well, it prints out we, and then it calls the function uh-oh. And then, okay, so we just go up here, and then what do? Well, we print out we, and then we call uh-oh again. And then so that means we go here, and then we go, oh, okay, print out we, and go to uh-oh again, and so on and so on and so on. And if we call this once, what are we going to expect to happen? Well, like we saw, it ends up making like an infinite loop, right? Like it just keeps calling, the function just keeps calling itself. It keeps making call frames and pushing them on the stack. Function will cause run. Look, it even gave us a warning. Look, uh-oh, recursive on all control paths. Function will cause runtime stop. Look at this. C++, even our Visual Studio was even like, you're not gonna like this. But I'm gonna do it anyways. And it's just going wee. So let's stop that. In fact, I'm gonna run again in debug mode so we can see the call stack. Takes a second to always set up the thing in debug mode. All right, I'm gonna pause it. And what? What the heck? You know what? I'm gonna put a breakpoint in, and then we can we'll be able to explore things better. There we go. All right. So I'm running debug mode. All right, what do we see? Well, the call stack. Well, in the main function, we can see right here, it's hard to see, but this is the main function. And then right here, it says what we called uh-oh. And we're stopped on line 17. We see nothing printed out. If I say continue, we get one we. Great. And then what happened though? Well, we called uh-oh again. So we made another call frame and pushed it on the stack. Made another call frame and pushed it on the stack. Made another call frame and pushed it on the stack. Made another call frame and pushed it on the stack. And so on 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 and so on. I'm going to delete the breakpoint and say continue. And it's just going to run forever until our computer goes, you know what? I've had enough of this. Your stack's too big. Goodbye. And this is what we call a stack overflow exception. In fact, I'm going to undo to turn it back into the counting version. So what are we going to do? Well, we pass it the number 1. And if 1 divided by 1,000 is 0, if it's a multiple of 1,000, I guess I could start it at 0. Print out n. And the only reason we're doing this is because printing out stuff to the console is actually really slow. So instead of printing out every number between 0 and however high we get, I'm only going to print out 1 every 1,000 just to save time with the prints. So I'm going to pass it the number 0. Is 0, okay, yes, that's true. Wait, is it? No, because 0 divided by 1,000 is 0, remainder 1,000. I guess it won't be. And then what are we going to do? We're going to pass n, which is 0, plus 1. So the next time this gets called, n is 1, and then n is 2, and then n is 3. It's basically just going to count. So let me rebuild this. Uh-oh, what did I do wrong? Oh, I must not have closed. Must not have closed the console properly. Okay, here we go. And let's run it. Oh, I guess 0 did work just fine. So look, we got to 0, 1,000, 2,000, 3,000, 4,000, and then eventually we were just like, no. And it even said exited with code negative whatever the heck that is. So I'm going to rerun this again, but in debug mode. And what do we see? Unhandled exception at whatever there, class Stack Overflow. So Stack Overflow exception. That's where Stack Overflow comes from. So we just kept pushing things onto the stack. And that's a problem because the computer's going to be like, okay, well, no, you're using too much RAM. Because this, every time we push something on the stack, we need to make a call frame, which takes some processing power. Then we need to put it onto the stack, which takes up memory. And if we let this run forever, our computer's going to run out of memory. We're going to be in big trouble. So this is problematic. Okie dokie. So that is an example of recursion. When you have something, like when a function calls itself, or when you have something that is defined in terms of itself, and you might think like, wait, what? Look, like what is, if I get rid of this and just have it count and it doesn't print anything, what is the function uh-oh? Well, the function uh-oh is uh-oh. So like uh-oh is defined as itself. Like it's self-referential, which is kind of weird, but it's also cool. At least I think it's pretty cool. All right, so recursion. What is recursion? See some examples, see where it's awesome, see some pitfalls. Awesome. Okay, actually, before we even do this example, which makes a lot more sense if we are in a lecture hall, which we are not currently, but are there any questions about recursion before we go? All right, well, that's awesome. So I'm curious. On my screen, I see like Aiden's first, then Alex, then Cole, then Dante, then Faith. Is it the same order for everybody? Someone tell me. Yes, sweet. All right, perfect. Here's what we're gonna do. We're gonna do an amazing exercise. Here's what I wanna do. I wanna know how many students are in this room. Obviously, I know it says participants is 16. Obviously, I see that, but let's pretend I don't. And I'm too lazy to count, okay? So here's what I'm gonna do. I'm gonna ask Aiden to tell me how many people are in this room because I wanna know how many people are here, how many students are here. But I'm lazy, so I'm gonna ask Aiden to do it. But here's the thing. Aiden's also really lazy too. Aiden, I hate to tell you, you're lazy. Because here's what you're gonna do. You're gonna say, well, if I knew how many students were below me in the list, all I have to do is tell James however many students are below me, plus one more, which is me, which is Aiden, right? So if Aiden knows that there are X students not counting him, then he just needs to tell me that it's X plus 1. Would you agree? Does that make sense? Say yes. Of course it makes sense. So here's what you're gonna do, Aiden. You're gonna ask Alex, hey, Alex, how many students are there below you in the list? And Alex, you're really lazy too. I hate to tell you, you're really lazy too. But here's what you're gonna do. So Aiden has asked you to tell how many students there are in the class below you in that list. And just like Aiden, you're lazy and you go, you know what? I don't know, I don't want to count. I'm gonna delegate this question to someone else. And I'm gonna have them tell me how many students there are below me. And then I'll just add 1 to that and tell that to Aiden. Right? Would you agree that that would totally work? So here's what you're going to do, Alex. You're going to ask Cole, how many students are there? And Cole's not going to answer that. Cole's too lazy. So then we're going to have Cole ask Dante. And then Dante's going to ask Faith. And Faith is going to ask Felix and yada, 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 yada. Eventually we're going to get down to William. And William's going to go, okay, well, Victoria wants to know how many students there are below me in the list, including myself. So I'm just going to ask Yagmir how many there are. And then I'll just add 1 to it and tell Victoria. But William, like everyone else here, like me and like everyone else above you in this list, you're really lazy. So you're going to ask Yagmir how many students there are. So finally, when you ask Yagmir, you're going to say, okay, how many students are there? And Yagmir goes like, well, there is no one below me. So I just need to tell William 1, right? And if William knows that there are 1 students below him in the list, he just needs to tell Victoria 2. And then Victoria, all you need to do is tell Cole 3. And then Cole, whose name here is Thomas, is just going to tell Samantha 4, 5, 6, 7, all the way up. So let's do this exercise, all right? And we're going to do it in the chat. As contrived as it'll be, we're going to do it. So I'm going to start and say, okay, Aiden, how many students are there? And what are you going to do, Aiden? Maybe you're not here right now. Aiden, are you here? Or are you ruining the exercise? Okay, you're here. So what are you going to do? Well, you're going to ask Alex how many students there are below him plus himself. So ask Alex. Type it in the chat. I know how silly this is, but type it in the chat. We're going to go all the way down and we're going to do it. Come on. Oh, now you're just ruining the exercise. Hey, literally just type in the chat, Alex, how many students are there? Alex, there you go. Perfect. Really, it should be like below you plus yourself, but that's okay. And now, Alex, you don't know. So you're going to ask Cole. So type that in the chat. Everyone get your type thing ready so you can hit enter at the appropriate time. And this is a great way to find out who's actually paying attention. Cole, how many peeps we got? All right, Cole, you're going to ask Dante. So ask Dante. All right, Dante, you're going to ask Faith. All right, maybe Dante's not here. There we go. Everyone get your typed message up ready. So Faith, you're going to ask Felix. Perfect. Felix, you're going to ask Gabe. Perfect. Keep going. Ask Jared. Ask Johannes. Keep going. Keep going. Keep going. Okay, well, everyone did it, I guess. Wait, no, keep going, keep going, keep going. Maybe we found someone sleeping at their keyboard. All right, well, let's assume Nasli asked Samantha. Samantha, ask. Okay, there you go. Yeah, okay, perfect. Ask Samantha how many students there are. Okay, is Samantha here? All right, there we go. Okay, perfect. Tom, yeah. Victoria. Wait. Maybe she's got people in different order, because Victoria should be asking William. Maybe Victoria has a different order or something, and that's why she was confused. William, okay, cool. And then William asked, yeah, perfect. Now Yagmir. I got nothing. Bingo. So what are you going to say? You're going to say like, well, all the students below me in the list plus myself is how many? Well, 1. So tell William 1. Perfect. Now, William, you're going to say, well, okay, there's 1 below me plus myself. That's what? 2. There. There. Keep going. Keep going. Nasli, it's you. There you go. Come on, Alex. Perfect. So now, Aiden, you tell me 16. Fantastic. Now I know there's 16 people. Now this contrived example, that is a perfect example of recursion, as silly as it seems. Look. You're asking me to solve a problem? I'm too lazy. I'm gonna ask someone else to solve this problem for me. And then that person's just gonna solve it until the problem gets broken down into such a silly, simple little problem that it's trivial to answer. Like, Yakmer, how many students are there? Well, 0 plus me, 1, done. That's called like the base case, the bottom. You'll see that in this example of recursion. We started at the top and we go all the way down. And then we hit that base case and then we go back up. And someone's making fun of the fact that I don't know how many letters in the alphabet. You're asking computer science kids to count. We don't know how many letters are on the alphabet, but maybe we can count. Who cares about letters? Maybe we can count. So that's our recursion example of going all the way down. And then look, if I know the answer to this question, I could answer it. If I know how many students there are below me, I could answer how many there are below me plus myself. That's easy. But I'm too lazy to figure this out. So I'm gonna ask someone else to do it for me. So I'm gonna make another function call to someone else. It's kind of like if we go back here, it's like, what comes after 0? Well, I don't know, but ask this guy to tell me. And then it'll be like, 1. What comes after 1? Well, I don't know. Well, 1 plus 1, well, that's 2. You know, it's the same idea, except this has no base case and it just goes down forever. So that's, if we were in lecture hall, what I would have done is I would have pointed to the back row and we would have done the same exercise at how many students in that row or something. All right, so recursion. By the way, I want to say recursion is one of my favorite things to teach. And chances are, if you're struggling with it, you're thinking too hard. Slow down. Slow right down. And if you think you've slowed down enough, you haven't. Slow down. So recursion. Define something in terms of itself. In a recursive definition, it's use the word or concept being defined in the definition by itself. So a recursion definition is a recursive definition. As annoying as that sounds, it is. So it includes a base case, typically, that defines something clearly without reference to itself. And I'm going to show you a fun little gag. If I want to know the definition of something, define happiness, right? Google will tell me. Let's do define recursion. Don't tell me it doesn't do it anymore. No. Maybe I just have to do recursion. Okay. I guess I just did have to do recursion. So it says, did you mean recursion? I can keep clicking it and I'll just keep going forever. Why? Because Google is a bunch of nerds that think this is funny. But anyways, recursion. It just keeps asking you. By the way, did you know you can do this one? Askew. And Google's results will be slightly askew. Do you see? Anyways, that one's fun. All right. So let's do an iterative definition. An iterative definition of like a group of people. Okay, so I could say like, well, a group of people is 2 people, or 3 people, or 4 people, or 5 people, or 6 people, or 7 people, or 8, all the way up to like infinity, right? Like I would, if I wanted to define this iteratively, I would need to define like to be as mathematically correct as possible. If I was defining this iteratively, I would have to like write out all possibilities. So I can look it up. But we can define it recursively by saying, well, a group of people is 2 people, or, and here's the magic, a group of people is 2 people, or a group of people plus 1 more person. So that's the base case, 2 people. But this is the not base case. This is the recursive call. This is a group of people is a group of people, but with 1 more person. So the base case has a clear definition. There's no ifs, ands, or buts about it. There's no ambiguity. There's no recursiveness in there. A group of people is 2 people, but then we have the recursive one that defines stuff in terms of itself. So what I mean here, let's do an example. If I have 6 people, right? And I'm asking the question, is 6 people a group of people? Well, I don't know. Because I'll check, I'll be like, well, it's not 2 people, but maybe it's this. Maybe it's a group of people plus 1 more person. All right, so a group of people plus 1 more person to make 6 would be 5 people, right? So we'd go down to 5 and we'd ask, well, is 5 a group of people? Well, 2 people, no. But maybe it's a group of people plus 1 more person. So what makes 5 minus, well, that's 4, okay. So we're going down. So 4 people. Well, that's not 2 people, but is 4 people plus 1 more? Like maybe it's that case. So we'll go check out 3. Is 3 people 2 people? No. But maybe it's a group of people plus 1 more person. So that would be 2 plus 1. So we'll go down to 2. 2. Is 2 people 2? Yes. Ah, look, by definition, 2 people is a group of people. So we know 2 people is group. So I now know if 2 people is a group of people, then a group of people plus 1 more person to make 3 people is also a group of people. And then if 3 is a group of people, that means 3 plus 1 more is a group of people, therefore 4 is a group of people. And if 4 is a group of people plus 1 more person, that means 5 is a group of people. And if 5 is a group of people plus 1 more person is a group of people, that means 6 is in fact a group of people. So we went down towards the base case, and then we were able to answer, and then we just kind of like project the answer back up. Let's define a sequence of characters iteratively. So, actually, no, yeah, what is an iterative definition of a sequence of characters? Well, oh, I hear a boop. What's up? Does anyone else start to feel like people is no longer a word? Yeah, kind of. I was getting tongue-tied. I was actually surprised I was able to keep pronouncing people during that rant. Especially group of people. So what is a sequence of characters iteratively? Well, that would be like 1 character or 2 characters or 3 characters or 4 characters or 5 characters or 6 characters. Or a sequence of characters is like a sequence of characters plus 1 more character is also a sequence of characters. So that's like the recursive one. But what's the base case? I guess maybe 1 character we could call a sequence. Maybe I'd call it 2. I don't know. I guess it depends on how we want to define a sequence. But I guess I could say like the base case would be like 1 character. You know what? No, let's say 1 character. That's our base case. I can change this out I want. Maybe it should be 2 characters. Now it's a sequence. Maybe it should be no characters, like an empty string is also a sequence. Maybe we could do that. But we could switch out the base case. The magic is the recursive step, where it's a group of characters is a group of characters plus 1 more character. So if I have 7 characters, is that a sequence of characters? Is that I wrote group. I should have said sequence. Sequence of characters. Is 7 a sequence? Well, I don't know. But is 1 less a sequence? And is 1 less than that a sequence? Is 1 less than that? All the way down to the base case. And then if we know that is, we just project the answer yes all the way up. Series of numbers. Consider the following series of numbers. 24, 88, 40, and 37. Let's define these recursively. Let's define a series, not these specific numbers, but let's define any given series of numbers recursively. So, a series of numbers is a single number or a number followed by a comma followed by a series of numbers. So, if I were to ask you which one's the base case, well, this one references a series of numbers in it, so that's probably the recursive one. And the base case, a lot of times you just look for something that's just like an answer. So a single number. Okay, great. So is it a number? Let's do this. So is this a series of numbers? Well, what was the definition? A single number or a number followed by a comma followed by a series of numbers. So is 24 a single number? No. Or is this whole thing a single number? No, it's not, right? So maybe it's a number followed by a series of numbers. But I don't know. Is this part here a series of numbers? Whoa, how did I do that? What? Okay, I don't know how I did that, but that was interesting. So is this a series of numbers? I don't know. So a series of numbers is a single number or a number followed by a comma followed by a series of numbers. Well, 24 is a number. So we know that. And it's followed by a comma. Therefore, it's a series of numbers if 88, 40, and 37 is in fact a series of numbers. So we need to answer the question, is 88, 40, 37 in fact a series of numbers? So 88, 40, 37. Well, 88 is a number and it followed by a comma. Therefore, it's a series of numbers if 40 and 37 is a series of numbers. Well, and then we have 40 and 37. Let's apply the definition. Well, 40, it's a number followed by a comma. So it's a series of numbers if 37 is a series of numbers. 37, apply the definition. 37 is a series of numbers because it's just a number. And if 37 is a series of numbers, then by our definition, if 37 is a series of numbers, then 4037 is a series of numbers, and then 804037 is also a series of numbers, which therefore means that 24, 88, 40, and 37 is, in fact, a series of numbers. Wow. So, actually, let's go back here quickly to see, now that I've ranted quite a bit, do we have any questions about what I was just talking about? Because it can seem crazy, but remember, the trick is to slow down and just follow the rules that you've been following since you started to learn how to program. Okay, well, I don't see anything, but again, of course, as always, just type something in the chat if you have any questions. Oh, so base case is number, no comma. Yeah, I guess it's just a number as I had it defined. Let's just make sure I had that defined the right way. Yeah, a single number. So a single number is the base case, I guess, in our situation. So that would mean, though, that would mean that if, here, I'm going to change to black so we don't get it confused. That would mean if for some reason I actually had like a comma after the 37 followed by nothing, by our recursive definition of a series of numbers, this would not be a series of numbers. Because if the comma follows the 37, but then there's no series of numbers after the comma, then the answer is, well, that's not a series of numbers. So, good thing we didn't have the comma there. All right, a list. We can define a list recursively. And some of you saw me do this when we were talking about the Haskell implementation of a linear search. But a list can be a recursive data structure. So it's not even like a recursive algorithm, it's like a recursive data structure where we can define a list in terms of itself. Which is weird because when we defined a list, it definitely wasn't like this fancy weird recursive data structure, right? Like we coded it, it was a bunch of things followed by other things, but we could define a list as a recursive data structure. Look, a list can be broken down into two things. The head of the list and the remaining bit of the list, where the head is like the first thing. So A is the head of the list, and then the remaining part of the list. So B, C, D, and E is a list. Or actually, I guess, is it a list? But so that's the head, that's the remaining bit. We call the remaining bit the tail, but the tail can be arbitrarily long. So the recursive definition of a list is, an empty list is a list. If we have a list that has nothing in it, that is a list, okay? There's nothing empty. Okay, an empty list is a list. That is the base case. Otherwise, it is a head, that's an element, followed by a tail, that's a list. So either it is an empty list or a head plus a list. But it's only a list if it's a head followed by a list. So if we have this, so the question is this a list by our definition? Well, A is a head followed by that list. And then I can take the remaining list, this part right here, I'm going to change the color again. This part right here, the question is, well, is that a list? Because if this is a list and A is a head, then I know this is a list. So then we go down here, we take the head out of this part. Well, B was the head of this sublist. So the question is this a list? Well, let's see if we can apply the list definition. Well, this is the head of that sublist. So is this a list? Because if this is a list, then this whole thing is a list, which means this is a list, which means that whole thing's a list. So we just got to keep going. So is this part here a list? Well, it's D followed by a list with just E in it. So, I mean, this is the head, this is a list, or pardon me, is this a list? Because if it is, then we know this is a list and we're good to go. And then, okay, well, now what? Well, we take out the E, and the tail, in this case, is a list, but with nothing in it. But, this is an empty list. And what do we know about an empty list? Well, an empty list is a list. So if an empty list is a list, then the head plus the empty list is also a list, meaning that this is there. Plus, the head plus this thing, which is a list, it means that this is a list. And then the head of this plus this part of the list means that this is a list. And then the head of the list plus this part of the list means that this is the list. And the head of the list plus this part of the list means that this is a list. Another thing that's interesting about recursion that you'll observe is, imagine I had actually asked if like Z, A, B, C, D, E. Imagine that I asked if this was a list, but you actually showed up late to class and you only started me going down here and looking at this. You'll see that like, well, if I know this is a list, then I know that Z plus, like I could build recursively up, right? Like I could just keep going. So because if this is a list and then this is a list, that means this is a list. And if I wanted to put something in front of it and call it the head, well, that would mean that the thing above me is a list as well, which is kind of crazy. Yeah, it's all lists. All right. Your recursive definition will almost always consist of two parts, your base case and your recursive part. The base case, that's the simple case that we could just answer. Then we have the recursive bit. This is the general case that describes all other cases in terms of, now I say smaller, but that's not necessarily true, but in terms of itself, in terms of another version of itself. So a recursive function could have multiple base cases or recursive parts as well, like maybe we have decisions to make. And it is technically possible to write a recursive function without a base case, except you're asking for trouble if you do that. Why have a base case? Well, infinite recursion happens easily, like we saw with that example of uh-oh. Just keeping an eye on the time. Yeah, there we go. And look, here is a joke inside of a textbook. If you look up infinite loop, it tells you to reference page 252, which is page 252, which will tell you to look up. So isn't that a funny joke? Look at that. Computer scientists are such nerds. Okay, going up and going down. Sometimes we can like start at the base case and build something. So if two people is a group, therefore 2 plus 1 more person is also a group. That means 3 people is a group, and then plus 1 more person is also a group, and so on. Or sometimes we like end at the base case. Like, well, is 4 people a group? 3 plus 1 a group? Is 2 plus 1 a group? And so on. And then if that's a group, then they're all groups. We can like project the answer back up. So sometimes like we start at the bottom and go up, and sometimes we start at the top and go down. All right. We can find a lot of mathematical things recursively defined. Raise your hand if you've ever heard of factorial before. Not factorio, factorial. 1, 2, a couple of people. And what does it mean? Well, if I ask you what 4 factorial is, what the heck? 4 factorial, well, that means 4 times 3 times 2 times 1. Bingo, exactly. So factorial, you usually write it with the exclamation point. That's the factorial operator. So the factorial of any positive integer is defined to be the product of all integers between 1 and n inclusively. So 1 factorial is 1, and then n factorial is n times n minus 1 factorial for n greater than or equal to 2. And it's only defined for positive integers. If you want to go to other things, we have different definitions for those things. We have like the gamma function and whatnot. But here, look, factorial, this is what we're defining. Here's the recursiveness, right? What this is saying is, look, if I ask what 4 factorial is, well, 4 factorial is equal to 4 times, what's 4 minus 1? Well, that's 3 factorial. And what's 3 factorial? Well, 3 factorial is equal to 3 times 2 factorial, right? And then based on this part right here, and then 2 factorial, well, what's that? Well, that's equal to 2 times 1 factorial. And what's 1 factorial? Oh, well, that's just 1. Why? Well, because it's written right here. This is the definition. 1 factorial is 1. So that means if 1 factorial is 1, 2 factorial is 2 times 1 factorial. We know 1 factorial is 1, so 2 factorial is 2. And if 2 factorial is 2, then I know 3 factorial is 3 times 2 factorial, which gives me 6. And if 3 factorial is 6, well, then I know 4 factorial is just 4 times 3 factorial. 3 factorial is 6. So 4 times 6 is 6, 12, 24. 4 factorial is 24. So you'll see that in order to know x factorial, we need to know x minus 1 factorial. That was supposed to be a minus 1, but it turned out all gross. I heard a boop. Shouldn't it start at 0 factorial equals 1? Some people will define it that way. Some people totally define it that way, but it's usually, like, it's just easier because if I do, like, okay, 0 factorial is 1, and then 1 factorial is equal to 1 times 0 factorial. 0 factorial is 1. 1 times 1 is 1. It's just like cutting it out. But people could, like, you could include that in the definition if you wanted. We were just cutting it out for simplicity. But you'll notice that, like, the factorial of any, like, x factorial is something we have to answer for any number, for any y greater than x. I don't care if you're asking what a billion or 100 factorial is. No matter what, I need to know the answer to 50 factorial. Which also needs to know the answer to 40 factorial in there, right? Because in order to know 40 factorial, I need to know 30 factorial. But in order to know 40 factorial, I need to know 30 factorial times 31 times 32 times, you know? So, and I could have been asking like a billion, 0, 0, 0, 0, 0, 0, 0 factorial. I still need to know 50 factorial at one point in time. So we need to know what x factorial is for any number, within the calculation of any arbitrarily large number y factorial. Like if I want to know y factorial, and x is less than y, but is also a positive integer, at one point I will have to have calculated what x factorial is. Does that make sense? Hopefully it does. If not, slow down and just think about it. All right. So what's 4 factorial? Well, we just did this. 4 factorial is 4 times 3 factorial. 3 factorial is 3 times 2 factorial. 2 factorial is 2 times 1 factorial. 1 factorial is 1. Oh, well, if we know what 1 factorial is, we just replace the 1. And then we know what this is. Well, that's 2, and then the 6, and then 24. Hey! And if I want to know what 5 factorial was, well, the great news is I already know what 4 factorial is. So it's just 5 times 24, which is what, 120? Is that right? 1, 2, 3, 4, 5, 7, 8, 9, 10, 12. Yeah, 120. So, iteration is repetition with loops. Recursion is defining something in terms of a smaller or simpler or just a different version of itself to do something that seems a little loopy. Recursion is an alternative to iteration, and anything you do iteratively, you can do recursively, and anything you can do recursively, you can do iteratively. Basically what I mean is if you ever write a for loop to do something, I can do the exact same thing with recursion. Or if there's something you did with recursion, you can write it in such a way that you use a bunch of loops. But just because you can does not mean you should. And we will talk about that next time because we're basically out of time and I don't want to start getting into this next bit. Yeah, so this is what we'll pick up tomorrow. Are there any questions though before we wrap up for the day? Okay, seeing none, I'll see you all tomorrow. Enjoy and goodbye.